All right, so this is the first real new lesson in this unit in which the focus is quadratic functions. And we've been dealing with quadratic expressions and equations already at times throughout this course in both the previous two units. But now the focus is really understanding these functions and understanding how they can be graphed and what changes to the equation make to changes to how that affects the shape of the graph. All things that kind of relate back to Math 10 with linear functions, but this is just more complex because we're looking at a more complex function. But I highly recommend, if you haven't done so already, to look through the previous video first, reviewing some of the core ideas from functions and domain and range with specifically to linear functions before trying to go too much in depth here. But a quadratic function is any function that can be written in this form. In essence, without just reading this all out, your variable, your input of your function is being raised to the power of 2 at some point, and that's the biggest power it has on it. Whereas linear functions, it's your inputs being raised to the power of 1, or just x. And so if I ignore this first term, this is a linear function. That was grade 10. Add an x squared or some, with some coefficient. Now it's a quadratic function, where again it says here, a cannot be 0. So because if a is a 0, then I have a linear function. But b, the coefficients b and this constant c can be any real number, anything. They don't have to be whole numbers. They can be 0. You don't have to have an x term. Just x squared in itself is a quadratic function. That's it. Which of these are quadratic functions? The only ones here that are quadratic functions, although as usual, I would recommend that you pause this video if you're looking at it for the first time and you make an educated guess on your own before I show these. But there's 3 quadratic functions. These 3 here. If you look at all of them, they all have the input x being raised to the power of 2 and nothing more. You may look at this e, again, has 2 to the power of 4, but not x to the power of 4. That 2 to the power of 4 is the same as 16. It's a constant. And that's what makes it quadratic. They all have the input being raised to the power of 2 and nothing more. If we look at a, that's a linear function. C, we call this a cubic function because x to the power of 3. And this is what we call a radical function. It's x is being square rooted. With that said, function a is grade 10. Functions c and f are part of pre-calc 12. All right, with that said, quadratic functions we deal with a ton in this course going forwards. And to be honest, we already have dealt with it a lot. So what does the graph of the simplest quadratic function look like? And the simplest quadratic function is just x squared. You can't get simpler than x squared and have it still be quadratic. And so if x is my input, then my output is y, or f of x. And so if I want to create a graph of something for the first time, a table of values is helpful. And if I just pick some numbers, I'm going to go from -3, going up in ones, to +3. And for example, when x is -3, the output is -3 squared, which is +9. Right? Negative times a negative is a positive. -2 squared is 4, -1 squared is 1, 0 squared is 0. And then 1 squared is 1, 2 squared is 4, 3 squared is 9. Notice I'm seeing these patterns repeat, which gives me a sense that my graph will be symmetrical. So plot these points. And so if I just plot these points, -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9. This is not my graph, because my graph is not just a few dots. It is a curve. But if I can't visualize this yet, I could just pick more points. I didn't have to pick these numbers here. But if you were to pick more points, what you would see is you get a nice curve. There's no sharp edges to this. That looks like this and keeps going up forever this way and is symmetrical. And we call this curve a parabola. And much like all linear functions form a line, all quadratic functions form a parabola. And this is the graph of x squared, or f of x, if I use function notation. Some things to take notice. This little point where it turned around, really important point. All quadratic functions have a point like this, and we call that the vertex. For this particular function, the vertex is at 0, 0. But not all quadratic functions have to have a vertex at 0, 0. That's a characteristic that lines don't have. Lines don't have a vertex. They don't have a point that turns. Really, really, really important, that vertex, which I could also see right there. All parabolas, all quadratic functions are, are symmetrical. And what I'm drawing now on this orange dashed line, this is the line of symmetry. It's a little hard to see. Let me make it a bit darker or bigger. There we go, a little better. This is the line of symmetry. If you imagine a mirror being placed on that dashed orange line, this graph would be symmetrical on either side. And so we call this the axis of symmetry. And this particular graph is an axis of symmetry at x equals 0. And domain and range, thinking back to the last lesson, domain is a description of all the numbers I can put into a function. In this case, whatever number I put in, I square it, I times it by itself. You can times any number you want by itself. You know, you've seen I've taken negative numbers times themselves are positive, positive numbers times themselves are positive, which means I can put any number I want into here, so the domain is all real numbers. The range, however, is not, because I don't care what numbers I put into this, I'm not going to get negative numbers out. And I can tell by looking at my graph. My graph goes up forever, but it doesn't go down forever. You know, the lowest point it ever gets to is the x-axis in this case, so 0. So the range is not all real numbers. The range is all numbers greater than or equal to 0. So again, I can put any number into this function, but I can't get any number out of this function. Before I go on, let me just go into Desmos here and show you a kind of a nicer version of this graph. I'll leave it like this. Let me just, there we go. So this is just, this dashed curve is what I just sketched out. Notice if I zoom in closer to the vertex, right, there's definitely no sharp points. In fact, if I zoom in enough, it looks actually horizontal, but I've really zoomed in a whole bunch. So it's a curve. There's no sharp points at all. It's all a nice smooth curve. And if I zoom out more and more, you can definitely see, yeah, there's nothing below the x-axis, but it just keeps going up and up forever. We call the shape a parabola. And this basic parabola we now have sketched into our notes. This x squared is something we want to memorize. We want to, we want to be able to know what x squared looks like without making a table of values. You want to know the graph of x squared goes through 0, 0, 1, 1, 2, 4, 3, 9, and it's symmetrical. It doesn't take much to have that down pretty quick. But we really don't want to make a table of values much going forwards. OK, so now the question is, if I take this equation x squared and I alter it in some way, what changes will that make to the graph? That's what I have here. And so if I take x squared and now I have x squared minus 1, what change will that make to the graph? Or plus 1 or plus 3? That'll change the graph in some way, but how? Well, if I just go to Desmos here. So I'll leave x squared as a dashed line. But if I, where was I? Here we go. If I turn on this graph right here, what you see now in purple, this is the graph of x squared minus 1. And we see in the dashed line in red is x squared. And if I zoom in more, these are the exact same curve, just the graph in purple, x squared minus 1, has been moved 1 unit down. Now, if you look at it and you think, oh, the graph in purple looks wider, that's an optical illusion because you're just seeing more of it because it's moved down. But they are the exact same shape, just one has been moved. Hold on, let me adjust my zoom settings here. There we go. They're the exact same shape. They're congruent. Just the graph in purple, x squared minus 1, is just 1 unit down. We say it's been translated 1 unit down. But that's the difference it makes. And if I add 1 to it, it's the exact same shape, but translated 1 unit up. And if I add 3 to it, it's the exact same shape, but translated 3 units up. And so anytime you have x squared and you just add a number or subtract a number, as we've seen, it's just going to take that exact same graph, but translate it up or down by whatever the number that is. So kind of summarize it right here. For minus 1, we say it's translated. And the word translated just means basically you slide it around. You don't flip it. You don't rotate it. You don't stretch it. You just move it. Translated 1 down compared to x squared. 1 down is what I care most about. This has been translated 1 up. And this has been translated 3 up. OK, if you look at the row below, it's the exact same operations in a different order now. Here I'm subtracting 1 before I square. Here I'm adding 1 before I raise it to the power of 2. Here I'm adding 3 before I raise it to the power of 2. If you compare the ones above, the exact same operations. I'm raising to a power 2. I'm subtracting by 1, for example, for a of x. But now the order is different. Again, order of operations here, first you square, then you subtract by 1. Here you subtract by 1 first, and then you square. So what difference does that make? Well, let's see. If I go back here, and I'll go back to Desmos, turn this off. Here's the graph of x minus 1 all squared. Notice it is congruent. And I think it's quite nicely, clearly congruent to what we started with. It's the exact same shape, but it's been moved, translated 1 to the right. And if I add 1 before I square it, it translates 1 to the left. And no offense to the number 1, but there's nothing special about it. So if I add 3, hopefully you can now predict it's going to move 3 to the left. So again, when I subtracted 1, you saw that. When I added 1, you saw that. And when I added 3, it was like that. And again, if I add 5, it'll be translated 5 to the left. And so to summarize this, and again, I'll write the word translated one more time, but I'm getting kind of bored of writing it. So this has been translated 1 to the right. And if I add before I square, it moves 1 to the left. And if I add 3, it moves 3 to the left. And if I subtracted 20, it would move 20 to the right. And so with that said, when I add or subtract a number to x squared, it does move it up or down, left or right. And where it moves depends on whether I'm adding or subtracting and where I'm adding or subtracting. If I'm adding or subtracting outside the x squared, then it moves up or down. If I'm adding or subtracting inside the square, then it moves left or right. So what if I multiply by some value, like these here? Or I'll focus on these 3 here, g, h, and I. So what if I have x squared, but I just multiply by a 2? I'm not adding 2. I'm multiplying the whole thing by 2. What difference does that make? Well, let's see. Turn these off. Again, what you see in red is x squared. What you now see is 2x squared. Notice it hasn't been translated, it hasn't been moved around, it's been stretched. And we call this a vertical stretch, vertical expanded by a scale factor of 2. What does that mean? Well, if you pick any point on, for example, 1, 1, right there. Oh, come back. There we go. On x squared. Up here, I have another point, a corresponding point, but now the y coordinate is twice as high. There we go, 1, 2. Or if I look right here, find this nice point right here, this goes through 2, 4. If you look at the graph of 2x squared, it's going to go through 2, 8. Every y coordinate has doubled. And that's what's happened here. By multiplying by the x squared by 2, all my outputs compared to x squared, all my y values have been doubled, have been multiplied by 2. And what happens is you see a graph like this, in which if I zoom out, you see it's, they're very, very similar, but it hasn't just been moved around. It's not been translated. It's been stretched. The vertex is in the same place. And so we call this a vertical expansion by a scale factor of 2. And pretty soon I'm going to get lazy, and I'm just going to write vertical expansion by a scale factor of 2. I'm going to write this SF. And so if you have a 3 in the front, that's going to be a vertical expansion by a scale factor of 3. But what does that mean? That means all my y coordinates will now be 3 times higher than x squared, which means the stretch is going to be even more. But it's still going to go through 0, 0. Because again, if I go back here, when we're dealing with the vertex, both these functions right now have the same vertex. And that's because they both have a y coordinate of 0 right there. I don't care what you multiply 0 by. It's going to say 0. But notice if I now turn off that and put this on, in fact, I'll leave them both on. What you see in black is 2x squared. What you see in solid red is 3x squared. Notice it's the same idea. It's been stretched more. And for example, it now goes through 1, give me this graph. Here we go. It goes through 1, 3 now instead of 1, 1. And it's going to go through 2, 12, right there. Whereas x squared goes through 2, 4. 12 is, the y coordinates are 3 times more. And so as you can probably guess, if there's a 1/2 in the front, we call that a vertical stretch by a scat factor of 1/2. But what does that look like? Well, actually, it's going to be what we call vertical compression. Why am I suddenly changing up the word expansion to compression? Because all my all my y coordinates are going to get smaller. If you multiply a number by 1/2, they get closer to 0. And so in practice, it looks like this. So turning off the previous ones, and here is 1/2 times x squared. And again, if it looks random, just pick a point on x squared. I'll look at 1, 1. Nice point, 1, 1, where there you are. And if you look at the graph in blue, it goes through 1, 1/2. Because all the y coordinates have been multiplied by 1/2. And multiplying by 1/2 same as dividing by 2. Or maybe a little more pleasant, compare on the graph of x squared, 2, 4. Notice the graph in blue, 2, 2. The output, instead of being 4, is now 2. It's half as much as before. And so we call this a compression because you can imagine all your y coordinates being squished down closer to the x-axis, whereas before they were expanded. So these two are expansions. What I have in blue is a compression. And so if I compare this, go back here, when I multiply by a number bigger than 1, like 2, 3, anything like that, I have an expansion. When I multiply by a number between 0 and 1, I have a compression. And so lastly, before I summarize this and then a final problem, what if I throw some negatives into here as well? What if I have x squared but just throw a negative in the front? Well, that will look like this. Let's turn this off. There we go. It's been flipped upside down. All my outputs have now been changed sign. So every single y coordinate I saw in x squared, for example, this point right here, 2, 4, is now at 2, -4. The x coordinate's the same. Now the y coordinate is negative. The vertex is still the same because, again, 0 isn't positive or negative. You change the sign, it's still 0. And we call this a vertical reflection. But I'll put in brackets, it's been flipped upside down. But we call this a vertical reflection. Or you can say it's been reflected on the x-axis, which means, ooh, that's kind of messy writing. Which means, if I go back to Desmos here, if you imagine there being a mirror on the x-axis, these two are reflections of one another. I prefer the phrase vertical reflection because it's just less things to say than reflected on the x-axis, but they're equivalent. And so the last two examples are just kind of combining these things together. So for example, this one here, I have a vertical reflection and it's moved up 1. So vertical reflection and up 1. So try to visualize what you think that looks like. Think about x squared. Reflect it vertically, flip it upside down, and then move it up 1. And what you get is this. It's been reflected vertically, and it's been moved up 1. And lastly, before we summarize this, there's a negative in front, so that's going to be the vertical reflection. But we're adding 1 this time before we square, so it's going to move 1 to the left. So try to visualize that before I show you. Imagine a parabola, imagine x squared flipped upside down and moved 1 to the left. And hopefully you are visualizing this. Reflected vertically and translated 1 to the left. So, to summarize, if you have a quadratic equation in this form, and we call this vertex form when you have an equation written in this form. We're going to hear that phrase a lot more later on in this unit. But the number, this a, I'm calling it, whatever we're, that number there that's in the front, that affects the vertical stretch. Vertical stretch by a scale factor of a. If there's a 2 in the front, the scale factor is 2. If there's a 3 in the front, the scale factor is 3. If it's a half in the front, the scale factor is a half. As well, I'll say if a is greater than 1, then we call this an expansion. The y-coordinates are being expanded out away from the x-axis. If a is between 0 and 1, like a half. Ooh, sorry, I wrote that down. That makes no sense what I wrote down. Between 0 and 1. There we go. Call this a compression. All your y-coordinates are being pushed towards the x-axis. And again, we've seen examples, just a few examples, but examples of all of these. And lastly, if a is negative, if we have a negative number there, then there is a vertical reflection. So that one number in the front tells us a lot. And if you had a number like -6, it's being reflected vertically and stretched by a scale factor of 6. So it's flipped upside down and stretched a whole bunch away from the x-axis. Compared to that, these other two are relatively simple. That p, whatever number goes there, that affects what we call a horizontal translation. And in general, if we're adding a number, so I'll say if p is greater than 0, it's moving to the left. If we're subtracting a number, or if p is less than 0, it's moving to the right. And finally, q and y, a, p, and q, because that's what the textbook's using. It doesn't really matter. I can pick any variables I want. I'm just going to be consistent with the textbook. And so the textbook uses q to represent the constant that's being added or subtracted separately from all the power of 2 and all that stuff. And so it represents a vertical translation. In general, if that number q is greater than 0, which means you're adding something, it goes up. If that number q is less than 0, which means you're subtracting something, it's going down. I cannot overestimate how important this is right here. For this class and for pre-calculus 12, understanding transformations, understanding how you can take an equation and change one of the parameters in it, and visualizing the change in your head before you actually graph it using technology or on paper is so important. And we did the same thing with lines in Math 10. Just there's more to look at here because it's a more complex equation, but so incredibly important. So if there's any aspects of this you're not sure about, fair enough, it's the first lesson. But this forms the foundation of the remainder of this big unit in this course, and is crucial for pre-calculus 12. So really, really important lesson. This is not a lesson that you kind of accept being a bit confused and just move on. With that said, sorry, I forgot what I have in my notes. Let's now visualize the basics of these graphs here without using technology. So I want to sketch each of these, what we have. So for example, x squared minus 3, I can visualize this as being the exact same as x squared, but translated 3 units down. And so what would that look like? Well, x squared looks something like this. So imagine that 3 units down. So now it's going to look something like this. And I'll just label this point here at -3. There we go. Again, visualizing x squared, which we had in our notes earlier, just move 3 down. What about here? I have a negative in the front and it's 3 down. So that means it's going to be similar to this graph right here, but there's a negative in front of x squared, so it's going to be flipped upside down. So it's going to look something like this. It's still going to be at -3, but now it's going to be opening down. Or you can imagine the graph of x squared with a negative in the front. That's what I'm showing in red. Move 3 down. Right? That's what I'm kind of sketched out in red. Whereas before in red I had just x squared. And so lastly here, I have negative x minus 3 squared. This time the minus 3 is being squared as well. It's not after the power of 2. So here again, I want to visualize x squared flipped over. But then when I subtract 3 before I square it, that's going to move it 3 to the right. So I want to imagine this being moved 3 to the right, so it's going to look something like this. And so keep in mind, what I just did, I sketched really actually pretty good graphs considering how quick it was, without making a table of values, without going into Desmos, just by understanding what x squared looks like, and then understanding these transformations. And again, I'm doing it pretty quickly because you can pause this and go back and whatnot. But so important. Okay, our goal is to develop a feeling for how changes to these equations create changes to the graphs without just having to plot a whole bunch of points on a graph. Okay, and now the final problem. Very similar to the final problem from the last lesson. If I have x squared and I just multiply by some number a, and I change a from -5 to 5, how will that change the shape of these graphs? Or what will change and what won't change? And so, again, very, very similar to the final problem from my review of lines, of linear functions. But imagine I have, again, x squared, but I have some number in the front, a coefficient that changes from 5 to -5. As it changes, how will the parabola change? And again, ideally, we can visualize this before I can show it to you. That said, ideally as well, we can visualize what won't change. So what I know what won't change is the vertex. I know no matter what a is, this is always going to have a vertex at 0, 0. Because the only time a vertex will change is when we add or subtract some number. I'm never adding or subtracting. So the vertex is always going to be at 0, 0. And again, so I know all these graphs are going to be, they're all going to go through here. If I just sketch out, this is x squared. So, but what if a is going 1, 2, 3, 4, 5? Well, I know the bigger it gets, the a gets, the more it gets stretched. So it's going to keep getting stretched more and more this way. And I know when a gets closer to 0, it gets compressed kind of this way. When a is into the negatives, I know it's going to be also reflected upside down. And as a gets more and more negative, it gets reflected upside down and stretched. So I'm describing a lot of change here. But one thing they all have in common is they all have a vertex at 0, 0. Because no matter what a is, I'm never adding or subtracting a number. And that's only when we add or subtract a number does the vertex slide around. So with that said, when I'm visualizing in my head, I can show you right here in a moment. There we go. So what you see right here is x squared. And in fact, what you're also seeing is ax squared, but a is 1. So now let me make a bigger. So as I make a bigger and closer to 5, notice it looks skinnier and skinnier, but it actually goes on forever to the left and the right. So it goes on forever, but it's getting stretched vertically more and more. At this point, we call this a vertical expansion by a scale factor of 5. Notice this graph in red goes through 1, 5 instead of 1, 1 for x squared. Really what you're seeing in red is all the points on x squared, or the y coordinates, are now 5 times higher. But let's bring a back down. So let's bring it now closer to 0. Notice a is now at 1, so the two are exactly the same. When a is between 0 and 1, we call these compressions. The closer a gets to 0, the closer it gets to being a horizontal line. When a is exactly 0, it's horizontal, and then once it's into the negatives, it gets reflected and stretched. So if I let this kind of just play and move on its own, you will see that once a gets into the positives, it's now above the x-axis. Now the larger a gets, the more and more vertically expanded it gets. But notice the vertex has never changed. And then again, now it's going to start going back down. The closer a gets to 0, the more this gets compressed towards the x-axis. And as soon as a goes into the negatives, it is reflected. And just kind of goes back and forth. So what you're seeing here is a dynamic visual image of all these different vertical stretches. Okay, there's a lot in this lesson. And again, it's the first part. We'll keep building off it. If everything seems really straightforward so far, then be humble about it. But chances are, not everything is so straightforward. And that's OK. It's the beginning of this unit. But we do, there is no more important unit in this course than quadratics. But a good place to stop here.